Hi everyone, welcome to our YouTube video. This is our signal network and system project, and this project will be developing a noise cancellation and an echo suppression device. The fundamental challenge we tackled in our project is the noise problem in modern audio systems. Simply put, noise is any unwanted acoustic signal that contaminates the desired audio, severely degrading signal quality and reducing how well we can understand speech. This interference is complex because it can originate from three main sources: environmental sounds like traffic and crowd chatter, electronic disturbances such as static or circuit hum, and critically, unintentional acoustic reflections, which we know as echoes. To effectively fight this dynamic and ever changing interference, we cannot simply rely on simple and fixed filters. We need a system that can continuously detect, analyze, and learn the characteristics of these noises. A system capable of adaptive noise cancellation. Now, after understanding the complex nature of noise, the crucial first step is detecting noise in signals, a process essential for effective filtering. We employ three core methods. First, statistical analysis, where we use the signal to noise ratio, also known as SNR, to quantify the amount of noise relative to the desired signal, giving us a hard metric for quality. Second, spectral analysis. It allows us to examine the frequency spectrum to identify specific and extraneous frequency components like a high pitched hum or a low pitched rumble that do not belong to the intended speech. And finally, thresholding involves setting an amplitude level to classify any signals below or above that boundary as potential noise requiring attenuation. Why are these detection methods so vital? Because they directly enable the technologies that define modern communication. This adaptive approach is what powers active noise cancelling headphones, allowing them to eliminate persistent ambient sounds during travel. It's essential for professional voice recording, ensuring clear vocal capture by removing studio background interference. And perhaps most importantly, it dramatically enhances video conferencing, where advanced noise suppression ensures remote meeting and online learning remain clear and effective. These applications prove that our sophisticated noise detection strategy is not a luxury, but a necessity for delivering high quality audio across all modern systems.
Moving beyond noise, our project also tackles another critical communication issue: echo suppression. An echo is essentially a delayed and attenuated version of an audio signal that returns to the source and is most commonly in telecommunication or hands free devices. This happens when the person's own voice is played through a loudspeaker, bounces off obstacles in the room, and is then picked up by their own microphone, creating that confusing doublespeak effect. To effectively eliminate it, we first need echo detection. This involves identifying a delayed signal that correlates perfectly with the original transmitted signal. We achieve this by cross correlating the outgoing audio with the incoming audio. A strong correlation at a specific time delay tells us exactly where the echo is hiding. Crucially, our LMS adaptive filter inherently performs this detection by working to minimize the error signal between the original far end speech and the echo contaminated signal, allowing it to accurately model and then subtract the entire echo path in the real time.
Our project was guided by two core objectives to create a truly intelligent audio system. The first was integrated noise and echo suppression. We leveraged the powerful least mean square, also known as LMS algorithm, to simultaneously attack both distracting background noises and bothersome acoustic echoes. The goal here was not just to suppress them, but to do so while preserving speech clarity, moving us towards real time processing capability. A second and perhaps most significant objective was intelligent self adaptation. We designed an adaptive filter that could automatically identify and mitigate dynamic noise and echo characteristics directly from the input signal, meaning it operates effectively without any prior knowledge of the environment. This minimizes reliance on external reference recordings and allows the system to achieve continuous dynamic optimization even as the background noise changes, ensuring pristine audio quality in any varying environment.
Our system is designed to efficiently remove unwanted audio interferences, such as background noise and echo. Unlike conventional setups that require multiple reference microphones or channels, our design intelligently processes just one input signal and delivering high quality audio through adaptive filtering. Let's walk through how it works. Step 1. Single audio input. The system begins by accepting a single audio recording. This recording may contain a mixture of user speech, noise, echo, all blended together in one signal. Step 2. Interference detection. Next, the system automatically detects and analyzes the dynamic characteristics of unwanted components. It continuously identifies changes in both background noise and echo, whether it's a moving fan, keyboard typing, or reflection from nearby surfaces. Step 3. Adaptive interference cancellation. Here lies the core intelligence of the system, the adaptive LMS filter. This filter dynamically learns the pattern of the interference in real time. As each new sample arrives, the algorithm updates its internal filter weights to model and subtract both noise and echo components, leaving the speech untouched. The adaptation is continuous, meaning the system responds instantly to changing environments, even if the background conditions or echo paths shift mid-conversation. Step 4. Clean audio output. Finally, the processed signal is reconstructed as a distortion-free version of the original input. The result is clear: natural sounding speech free from both background noises and echo. This seamless real-time adaptation makes our system not only efficient but also highly practical for real-world audio communication, conferencing, and recording applications. In summary, from a single noisy input, our architecture intelligently detects, adapts, and delivers pure interference-free sound, ensuring clarity in every word you speak.
The core innovation of our system lies in the reference signal extraction method, where we intelligently derive all necessary baselines directly from the single input audio stream, eliminating any reliance on external references. This is a self referencing advantage that boosts our system's practicality in the real world. Our filter achieves automatic detection for both noise and echo by looking for distinct characteristics within that stream. For noise, it expertly pinpoints low energy segments where speech is absent to the sample background interference. Whereas for echo, it analyzes specific temporal patterns that indicate a delayed reflection of the transmitted signal. These extracted characteristics, encompassing both the noise patterns and the echo path, provide the LMS algorithm with the dual baselines it needs. This allows the LMS filter to dynamically lean, model, and effectively cancel both types of interference throughout the entire signal, making the signal highly adaptable to any acoustic environment.
The LMS algorithm is a fundamental and crucial adaptive filtering technique used in real time applications like our noise and echo suppression system. Its core strength lies in its ability to continuously adjust to changing signal and environmental conditions. The central principle of LMS is iterative optimization. It constantly adjusts the filter weights to minimize the mean square error, which is the difference between the desired clean signal and the current output. This allows the filter to adaptively learn and track changes in the signal, noise, and echo paths, making it highly robust in dynamic environments. This adaptation speed, however, is heavily influenced by the step size parameters. A larger step size accelerates the filter's convergence but increases the chance of instability and steady state error. Conversely, a small step size ensures greater accuracy and stability. Our optimal selection balances the speed and precision, ensuring the filter is both fast enough to track real time changes and stable enough to produce high quality audio.
The core engine for our noise reduction system is the least mean squares or LMS algorithm. It's the industry standard for noise cancellation because it continuously adopts its filter coefficients to model and subtract unwanted background noise. In the context of noise cancellation, we are focused on removing uncorrelated disturbances, unlike echo suppression, which targets correlated reflections. The LMS filter learns the characteristics of random ambient noise and dynamically filters it out in real time. Let's visualize this process using a simple block diagram with inputs being d of n and x of n representing the noisy signal and the reference noise sample respectively. The LMS algorithm works iteratively with every single audio sample following four key steps. Step 1: Sample buffer extraction. For the current time sample n, we collect the last m samples of the noisy input signal to form a vector x of n. This becomes our input window. Step 2. Noise signal estimation using the filter's current internal weights w. We predict the noise within that window. Y of n equals the w transpose multiplied by x of n. Step 3. Clean signal error calculation. We compute the difference between the noisy input d of n and our noise estimate y of n. This result, called e of n, is our estimated clean signal. Step 4. Filter weight adaptation. This is the learning step. We update the filter weights using the formula w of n plus 1 equals to w of n plus uh, 2 mu times e of n times x of n. This continuous sample by sample process minimizes the error e of n, refining our clean output with every iteration. By doing so, the LMS filter perfectly adapts to changing background noise characteristics.
While the LMS filter removes general noise by looking for uncorrelated patterns, its application for echo suppression is slightly different and incredibly elegant. In this case, the source of the echo, the far end signal, is actually available to us, making the LMS algorithm an exceptionally efficient solution. It works by dynamically adjusting its coefficients to model the exact path the echo takes through the air and back into the microphone. This process is broken down into four key elements. First, the input signal. This is the near end microphone signal which captures the local speaker voice plus the unwanted echo. Second, the reference input. This is the clean, uncorrupted signal sent from the far end speaker, which is the direct cause of the echo. We use this as a perfect reference for the adaptive filter. Third, adaptive filter estimate. This the filter uses the clean reference to generate an estimated echo component. This estimate is calculated using our filter's current weights. This estimated output is a model for the echo path. Finally, echo cancellation and weight update. We subtract the estimated echo from the noisy microphone input. This resulting error signal is our echo cancelled output, ideally containing only the near end speech. The LMS algorithm then adjusts the filter weights using the famous formula to continually refine its model, ensuring perfect cancellation even as the acoustic of the room change.
This process has been a powerful exercise in applying theoretical knowledge to a real world problem, and we thank you for following our journey. For those interested, you can find the code repository and processed audio samples and full documentation via the links given below. And thank you for watching.
Beginning with the explanation of the simulation of first audio system. Here this is first the UTS file, which includes the different important functions that are required for this program, for the simulation. For example, this is the loading file, which loads this in the stereo, not in the mono form, not in the stereo form, which saves the wave file in the given path that we want. This normalizes the signal to get the values from -1 to 1. This will compute the SNR. SNR is the noise to sound ratio. Here we get the value which is required. This will plot the waveforms in the subplot manner so that it is easier to compare. This will plot the spectrogram of the required output. Now this is the combining file, which will combine the two files, which is the speech file and the noise file. Here is the speech file.
Number 1. The birch canoe slid on the smooth planks.
And this is the noise. So now we'll have to combine both. First we will convert it into the mono form, which if it is in stereo it will convert it into mono. Now we'll adjust their lengths to be equal of the minimum of the both. We'll normalize this and make a primary form which will add the speech and noise form. So now first we'll have to run this file. has created the reference and the primary voice which is required.
Number 1. The birch canoe slid on the smooth planks. Glue the sheet to the dock.
Both the files have been added to the primary file, and now we'll have to run the NLMS, which is the normalized least mean square method for noise cancellation. In this, we'll first load these files, normalize them, and then this is the method where we run a for loop so that we get the error from the reference which is required. So it will calculate the reference and it will automatically adjust the preference waveform, primary waveform, to give us a output waveform. And let's run this and check it. We have also plotted the waveform and the spectrograph of the output. This will take just a few seconds. So this was the primary, which was the speech and the noise file. This was the clean, which was the expected output, and this was the expected output, and this was what we've got. We have saved this in the report form. Here is the clean output.
Number 1. The birch canoe slid on the smooth planks. Glue the sheet to the dock.
As you can see, there was minimal problem. So this was what we required, and this is C here. So now we'll take a look at the simple digital signal processing project on echo suppression using NLMS adaptive filter system, which is done in Python. Firstly, we'll input the two waves, which is the echo and the echo reference. This is what the echo sounds, and this is the reference that we are giving. So this echo is now identified and it will subtract from using the NLMS code. Then we'll get to know the clean echo suppressed output. First, we'll use the load input functions which are in the utils file. Here we'll first load the inputs using the sound file library in Python. We'll load the two sound files, echo signal and reference signal, along with their sampling rates as fs. Then we'll use the align signals function to align them so that both the signals are synchronized in time, and because the echo path also introduces other delay. Now to the core part of the NLMS system. This is the main function which was also explained in the previous section. This is used to first filter out this suppressed output, and also normalize using the normalize function. This is the normalize function. It will divide it by the maximum value. After processing, we will clip the output for 0.45 seconds so that we get a clearer output and a shorter output. Now finally we'll write this audio file using this write function, write audio. We'll give it the path, and this will save it in the desired location, which is the output reference. After running, this is how output sounds like. It just goes for a few seconds, which was the original echo, and which repeated to make the echo. Then yeah, this is done. We'll also plot the signal. This is how the plotting works like. We have synchronized as these are now in the synchronized form, and this is what the original echo was. NLMS is one of the most popular algorithms in DSP, and we are using this as a practical example of system identification. So after echo cancellation, let's move to another powerful DSP technique, noise cancellation using spectral subtraction. So this method directly works in the frequency domain, and it is one of the simplest and effective approaches. Uh, we are not using any reference for this one. It will automatically estimate the reference over here. The first step is again of loading the file. This time we'll use the Librosa library in the Python, as it has much more functions, inbuilt functions. The load file will load the uh, input noise outcome. This is how it sounds like.
Number 1. The birch canoe slid on the smooth planks. Glue the sheet to the dock.
This was same as the previous input. Now we'll use the STFT, which is the spectral subtraction method, short time Fourier transform. So we convert the signal in the time domain to the frequency domain using STFT, and this will also plot the wave spectrogram format so that we can get a visual uh, image of what is going on. It will also estimate using the low energy frames, the spectral subtraction method, and it will help to give the estimation to itself, which it will feed for itself. And this is how it was going to subtract from the cleaned waveform. It will this to use this as reference and then use it to give us the cleaned output. After running, uh, we'll get the desired output. Firstly, we'll look at the alpha and beta terms factors as well. Alpha is determines how aggressively we subtract the noise, and beta is a small constant to prevent effects and negative magnitude. So after reconstructing this signal, we'll finally take a look at what the main is doing. This is the STFT program method, and this is where we applied the noise gate. So this basically gives us this is the reference, not clearly the reference, but low energy frame. Below this, all the inputs, below this, all the noises are uh, filtered out. So this will give us the clean output, and this is how it
Number
sounds
1.
like.
The birch canoe slid on the smooth planks. Glue the sheet to the dock.
As you can hear, the most of the part was cleared out. So this was the not required extra uh, noises, and this is how it got cleared below that 0.005 threshold. We have plotted this using the plot waveform function. So in conclusion, we've used two different libraries, Soundfile in the previous one and now the Librosa library as well, to implement a complete noise cancellation system and based on spectral subtraction. Here the two parameters alpha and beta are the ones which keep the balance of speech clarity and noise removal.
We just saw the codes for both noise cancellation and echo suppression. I would just like to clarify the difference between these two. While both noise cancellation and echo suppression utilize the powerful adaptive capabilities of the LMS filter, their context and reference signals fundamentally differ. The primary distinction lies in the signal's origin. For noise cancellation, we are attempting to remove additive unwanted ambient noise that is generally uncorrelated with the desired speech. Therefore, the reference signal we use, such as the noise sample captured during a silent period, aims only to model that background interference. Conversely, for echo suppression, the interference is a delayed, attenuated version of a known signal. The clean audio sent from the far end speaker. This makes the echo source readily available, allowing us to use that clean far end signal as the perfect reference input for the LMS filter. In essence, noise cancellation removes unknown contaminants, while echo
To
suppression
conclude our
specifically targets
comprehensive
and
signal
models
and
the known
systems
signals of
project, we
fraction.
successfully implemented a robust LMS based adaptive filtering framework capable of dynamic noise cancellation and echo suppression, the efficiency of which is proven by the achievement of superior audio quality demonstrated by significant enhancement in signal to noise ratio, also called as an SNR, and echo return loss enhancement, also known as ERLE, and visualized through comprehensive performance metrics. Our core innovation is the intelligent self-referencing system, which allows the filter to continuously adapt to the changing interference without needing any external reference signals, which greatly boosts its practicality. Looking ahead, our project lays the groundwork for critical future enhancements. Looking ahead, our project lays the groundwork for critical future enhancements, primarily optimizing the algorithms for real-time processing integration to achieve ultra-low latency, exploring advanced adaptive algorithms like NLMS, RLS, or even deep learning approaches to further accelerate convergence, deploying the solution onto hardware like specialized DSP boards for standalone operation, and finally, incorporating the intelligent signal prioritization with voice activity detection, also known as VAD, for more precise filtering and better system efficiency.